All right, in the second part of this section, we're going to use Mathematica to help us understand the linear approximations and the differentials. So we're going to be using the function x minus 2 quantity squared, and our point of interest or tangent point is going to be the point 1, 1. So the first thing, again, just a little reminder from pre-calc, we don't even really need the computer to understand a basic sketch of this function. So if we were to start with y equals x squared, our famous parabola opening upward, vertex at the origin. Then x minus 2 quantity squared just moves that 2 units to the right. So now I have a vertex at x equal 2. Okay, so again, just a little reminder. And it says, will approximations using the tangent line at x equal 1 be over or under estimates, and how can we tell? So now let's just look at our graph of f of x. So let's say this is x equal 2, and here's our parabola. Sorry, my dog is chewing on her bone. I hope that that's not too distracting. And here's x equal 1, so my drawing, again, it's not quite to scale, but you'll forgive me, I hope. And here's my tangent line that I'm going to use to estimate values on f of x. So since the tangent line lies below the function f, that means my linear approximations are going to be underestimates. And by the way, why does the tangent line lie below the function f of x? Because f is concave up. Right? So since f of x is concave up, tangent line at x equal 1 lies below the function, which means the linear approximations I get from using the tangent line are going to be underestimates for actual function values. All right, so here's some code, and again, if you haven't already done this, you might want to pause the video and get this stuff entered in Mathematica. So let's see if we can understand what this stuff is. So first of all, hopefully it's clear by the name, but I've defined here delta y. That is the actual change, f of x plus delta x minus f of x, right? So this is the actual change in the function output. And next I have the differential dy. That is f prime of x times dx. So that is an estimated change in the function output. And just by way of reminder, and again, this is when x changes from x to x plus dx. This is also the actual change in the tangent line. Right, so we're taking the slope of the tangent line times the prorating amount dx of how much the x is actually changing. So just by way of reminder, f prime of x is the estimated change in f, but the actual change in the tangent line when x goes up by 1, that's what slope is. And then we're saying, but x can go up not necessarily by 1, but some amount dx. And if we multiply the slope by how much the x is actually changing, then we'll get the actual change in the tangent line value. So that's our differential dy. So let's think about what we can understand here. So this again, delta y 1 comma negative 0.1. That's a delta y value. So the 1 right here is telling us the x coordinate, and if we go back to our function definition, that's 1 comma f of 1, and we can very easily put 1 into our function value. 1 minus 2 quantity squared is also 1. So our point of interest is the point 1, 1. The negative 0.1 right here, that's our delta x, or our dx. So we're moving left 1/10 of a value. So when we get a result of of 0.21, what does that mean? Okay, so if we're on the function f of x, at the point 1, 1, and we move along the function let me not use the negative, I'll use direction here, and we move 0.1 units left, to x equal 0.9, we'll move up 0.21 units. This is on the function f of x, right? So again, delta y is about actual change in the function. Now the dy, the differential dy at 1 comma negative 0.1, right, says that if we evaluate that, we get a value of 0.2. This means if we're on the tangent line, and remember, when we're at the point of interest, at the tangent point, we're both on the function and the tangent line at the same time. And we move 0.1 units left to an x value of 0.9, 1.1 units to the left of x equal 1. We'll move up 0.2 units on the tangent line L of x. So in the first case, instead of being at 1, 1, we'll now be at the point 0.9, 1.21. So we've moved 0.1 units to the left on x, 0.21 units up on y. On the tangent line, I should say at, we'll now be at the point 0.9 on x, so we were at x equal 1 and we moved 0.1 units to the left to x equal 0.9, and we've moved up 0.2 units on the tangent line, so we'll be at the point 0.9, 1.2.